All right, so welcome to CS 280, 260. And my goal today is to basically go over, kind of high-level overview of what this class is about, and then kind of discuss some of the logistics, and then we'll start talking about the actual content. All right, so introduction. Okay, so first, so the main resource I would say for the class will be the class webpage. I posted a link on Bruin Learn. If you haven't seen it, make sure you see it. So all the, when the assignments are going to be out, when are they due, and everything else is on the class webpage. So we'll mainly use that for kind of coordinating things. Another important resource is going to be my office hours, which will be on Monday from 2 to 3 p.m. Okay. And we will also use EdSTEM for online discussions, questions. Officers are good because they're in person, they're relatively infrequent because once every week, but you get more in-depth discussions. EdSTEM, I usually respond within a few hours, if not even sooner. So you'll get quick feedback. And just to give you an idea of what you would see on EdSTEM, let's say we go there. Oh. Hold on, I want to show you. Because if you were like the page, it will look something like this. All right. And the main resource here will be you have actually code, right? First bit that current practice and download and do some demos as we go along. And also you have lessons page. If you go there, as we go through the course, each of these will be available for you to view. If you go there, you have the video link and the summary. So we'll use that a lot. Okay. So make sure you register for that class on this website. I might have got an email to you register. Otherwise, you can also sign up manually by writing the link on the class website. All right. And so the class also has two sections. So we have two sections. For the most part, there is no difference. There is the in-person class, in-person section, and there's also the MS online. So all the content, all the assignments, and the timelines, everything will be the same. And the recording, of course, tomorrow is available for everybody. You can access both. But there's a key at the plan for the online. Okay, so if you're online students, you can synchronize with your TA, you can learn and get them called. Okay. And okay. So the resources, officers, and let me say a few words of the grading policies. So for grading, you have 4 assignments. The assignments will have both theoretical and coding problems. Just 1 or 2 coding problems are not too complicated, but at least to understand the main concept so we can discuss. The dates are available on the course webpage. Again, there's something when you go there, you just show it once. So this is the course webpage, and you go here and see like grading assignments. So assignment 1 will be out April 12th. So we'll have basically an assignment every 2 weeks. Each assignment will cover 4 lectures, 4 lectures in 2 weeks. And the first one is worth 18 points. The last one is worth 15 points. It only has 3 lectures. Right, and then the final is as per university schedule on June 14th to 18th. Right. The final is 25 points. It covers the entire. Any questions about the gradient or? And class participation has 5 points. You know, and class participation just means that you're showing up for class, asking questions. Either in person there or either in person there or on this question. Okay, terms, please mute yourself. Okay, that's all right. And that's the main things I want to say about the class organization. 70 point. Final 25 point. Class. Is 5 points. Okay. And one more important thing I want to stress this is there are some prerequisites for this class. So prerequisites are here probably and is it better now? Someone on chat said no, audio is good. Okay. But can you all hear me if I turn off the microphone in the class? That's fine. I think that's the problem. Okay. All right. I'll maybe speak a little louder. All right. So make sure you have some knowledge of these things. And one way to test it is if you go to the class website, there is assignment 0. You don't have to submit it, but make sure you take a look at the problems. Okay. I'll make it public. So take a look at the problems there, and it has some simple questions about definitions and from linear algebra probability and algorithms. Make sure you can answer them. If you can't answer them or at least know what the questions are asking about, then come and talk to me immediately. I think it will require extra work if you don't have those prerequisites. All right. And let's see. Okay. All right. So with that, that's all I wanted to say about the logistics. I think it will run pretty smoothly as we go along. And let me now say what this course is about. So what are the main learning objectives from my perspective? The first thing I want to say is that it is not a pure machine learning class. So what do I mean by that? I mean, we are not going to study models and statistical bounds much in this class. Okay. Instead, we are going to mainly focus on, suppose you already decided what model to use under some consideration. In some cases, we'll also talk about reasons for choosing specific models. But once you do that, what algorithms do you use to train or test and other considerations for the model? Okay. So the emphasis is on algorithms used in machine learning. We'll touch upon some of the modeling issues, but we won't be digging deeper into them. We'll be digging much deeper into the the handful of algorithms that really underlie much of modern machine learning. In fact, we'll focus on maybe 6 or 7 algorithms, and then spend a few lectures each on every one of them, considering various aspects and things. And it is also not a course to teach latest tools or software. Okay. So, I intend this course to be so that once you know this material, you are going to design the next generation of tools and software. So if you want to do that, you need to know what are the things that are being used underneath the surface. Not just how to use them, but what's behind the actual infrastructure that we use to train many models. Okay. So let me see. And I think this is important for 2 reasons. One, you might have to tweak your algorithms when you start new models. And if you want to design the next generation tools, you need to know how these things function. All right. Okay. And in terms of the actual outline of the course, we will have roughly about 5 sections. So reasonably sort of modular, but there will be some continuity from one piece to the next, especially in terms of familiarity with various analysis techniques that we use. The first module will be on optimization. So we'll connect it to learning, what it means we'll introduce the basic model for learning, and then we'll switch to just an algorithmic question and study various algorithms for solving that question. Okay, so we'll do GD, SGD, and you'll know what these terms mean later on. The second one is online learning. This deals with a different challenge in learning when you don't see all of the data at once. So for roughly 3 lectures, then we will have principal component analysis, or basically trying to identify relevant features in a data set in an automated way. Okay. And then the last 2 are usually somewhat amenable to choice and sometimes change them depending on interest. Last year I covered what we call as graphical models, which are important in various applied sciences fields, and then privacy considerations. Okay, so this is a rough outline of the class. The core would be the first module, optimization, which will help us kind of address many of the other things as we go along. Okay. All right, any questions? All right, so if there are no questions, we can, that's kind of this overview of what we are going to do for this quarter. And let's get started with the actual content. And the first question I want to ask is, what is learning? Kind of a very broad, ill-defined question. So maybe let's just think of some examples of what we think of as learning applications these days. Can you tell me some applications and examples of what you think of as learning or machine learning or any such things? Yeah.
Determining if the problem is acknowledgeable.
That's that's actually where I was going to go to, but we haven't discussed it. So let's maybe think more in terms of applications. Okay, so we'll get to that in a little bit. What else? Yeah.
Maybe you have like a robot and wanted to follow a certain path to get out of the place.
So that's basically, let me call it planning. Right, planning problems. You have some, view of your surroundings or some information about some input, and you have to plan your actions according to that input. Okay. What else? Think of some application. Yeah.
Like a series of
classification is in fact one of the most important applications. Although, most of the time, the biggest advances in classification, at least in the modern age, didn't come from just studying classification alone. It's very helpful to focus on classification because it makes modeling much easier. And we will take that as kind of the starting point for our models and algorithms. What else?
Right now it's like generative stuff.
Generative stuff for sure. Generative models. Right, like you can think of image generation, text generation, and so on. Okay, and what else? I mean, yeah, go ahead.
Didn't Markov models can learn things too?
Sure. I mean, but in terms of applications, like let's say, even if you're thinking of something like maybe, so HMMs or hidden markov models are useful for classification, and they're also sometimes useful for generative models. Okay. So other applications, where learning kind of is happening either directly or implicitly. You might not realize it, but advertising has a lot of learning behind it too. And every time you open a website, it shows a bunch of ads for you, and which ads it's showing is predicted based on your history, your location, and many other attributes, right? Advertising can get really spooky sometimes. You message someone on Facebook about, maybe going to Iceland, your closest friend will start seeing ads for tours from Iceland. Okay, that has happened to me in the past. And recommendation systems. Like you watched a bunch of movies, and whenever you log into Netflix, it suggests, okay, watch this next based on your history. So all of these are learning problems. And at first look, you might think that this is entire, this is all in different domains, but ideally we would like to build generic techniques, right? Or at least models which can address these things, and then maybe tailor them to the specific application. Okay. And if you follow such a generic thing, of course, you won't get the state of the art, but it'll always give you a good starting point. And we need to know what these things are, right? And we can also categorize these applications into groups. Meaning, not all of these learning problems are, some of these learning problems are similar to one another than others. And one group, for example, is supervised learning. Supervised learning means you actually have data which is labeled. Someone gave you a bunch of images which are like, labeled. Okay, this is an image of a dog, this is an image of a cat, or even something more specific. This is an image of, a poodle and so on, right? And then you have to design your learning system based on that. So you have some supervised or curated data. And what's the kind of opposite of supervised learning? No surprise, it's unsupervised learning. Unsupervised learning means you don't have any labels. You just have a database of, lots and lots of images. And from this, you're trying to make something out of the data. Okay. And often, obviously supervised data is much more useful, but we have orders of magnitude more of unsupervised data than supervised data. Right? The number of labeled images is tiny compared to, let's say, the number of images on Google Images. Right? And there's also something called self-supervised learning. Which actually is really risen to prominence, especially in the context of generative models and image generation. Self-supervised learning is a little bit like saying, I have unsupervised learning. I don't have any labeled data, but I'll create some artificially labeled data by maybe hiding some part of my unsupervised data. I take a sentence, I just have a bunch of sentences. I hide one word from a sentence, and my task is now to predict this hidden word. Okay, so in some sense, I'm generating labeled data artificially by starting with unlabeled data, and I'm creating myself tasks based on this. Okay? I mean, that's how many of these large language models are changed. You mask some parts of your sentence and then try to predict them. You can do the same thing for images and many other stuff. And you can also have all kinds of things like semi-supervised learning, which is in between the two. There is active learning. Active learning means you're not just given the data set. You can go and seek out what you think would be most useful for you, right? Maybe you say, okay, I'm getting confused always between this particular cat and this particular dog. Can I ask somebody to label this, these images for me? Right? It's actually how we humans learn, right? You ask a question that you think would be most useful for you in updating your model. And there's reinforcement learning, where the learning is not happening in a static environment. Kind of like, what was suggested earlier, if you're trying to plan, to solve a maze or something, then you have to update your model based on your environment, which you don't have knowledge ahead of time. Okay? So all of these are, you can teach a single course on each one of these topics, right? But that's not what we're going to do. We're going to start with the simplest class to model, supervised learning, and use that as a starting point to develop some algorithms which are used across all of the other things. Okay, we'll talk about unsupervised learning a little bit towards the end when we talk about graphical models, but for the most part, we'll focus on supervised learning. Okay. All right. So let's start with the question: how to model supervised learning. Okay. And so there are various formulations of modeling supervised learning. One of the most important historically is what's called packed learning, probabilistic, probably approximately correct model. And let me, kind of describe it once, and then after that, we'll go on to something I think more useful, practical. But first, we need to know what we are learning or what we are trying to learn about, right? So let me say. So as I said, we'll always think of everything as an algorithmic problem, meaning there's an input and we want to get an output, right? And what's an input for a learning problem? So you have some data set. Okay. And what is the data set? You basically have some domain. Let's call it X. Think images, think text, maybe DNA sequences, whatever you have, right? Some domain. And you have, in the case of supervised learning, you have some labels. Right? I mean, labels could be, think images, text, DNA sequences, etc. And labels could just be, think, cat, dogs. Maybe you're trying to, and many other things. Okay. And a data set is just going to be a collection of pairs. You have some element from your domain, like an image, maybe a text sequence, maybe a vector, and then a label associated. Right? So you have a collection of n such pairs. And the assumption is that this is always in domain, and then the label is your label. Okay. And what are we trying to do? So what is our goal? What would be the ideal thing that we'd like to do? Any suggestions? Yeah. Let's see. Yeah, so I mean, you're given this collection of things. I tell you, okay, this is an image of a cat, this is an image of a dog, and so on. And next, I give you an image without any label, and we'd like to predict, right? So that's the, as general as it gets, and as useful, pretty much as useful as it gets. Given a new X that we haven't seen before, right? We want to predict. Okay. And I mean, this sounds very, very neat, but to make this question well posed, we need to make some assumptions. Okay. And what are some of those assumptions? Can you always solve this problem? Like if I just tell you, okay, here's my data set, here's a new thing, can you predict this label? Sometimes it doesn't make any sense. What if I give you just a data set of images and labels of cats and dogs, and in the test I give you a sentence? That doesn't make any sense. Right? You haven't seen a sentence before. It's a completely different problem. So there has to be some connection between your training data set, what you're seeing for your training, and what your test is on. I can't teach the entire course on machine learning and the test is on maybe network. That doesn't make any sense. Right? That will be cruel. So how do you formulate the fact that the test should somehow be connected to the data set? Any suggestions? Like how would you get this continuity that you're kind of learning and testing yourself on related problems? Yeah. That's a good way to verify your performance. But if you think about like, going and trying it out in the wild, right? You don't see the test example before. So can we do something more general than that? It might be a strong assumption to begin with, but I think it's a meaningful thing to start. Yeah.
You're going for, but you have to know that we like the label. We know that label, ground truth.
Even before going to the label, I think there has to be a connection within just the example that you see. Okay. Yeah.
Depends on the representation. But assuming
So basically, we want to say that whatever you're testing on is kind of coming from the same source as whatever you trained on, right? There's a pool of questions that you're trained on. Your test is going to be something related to that. And the way statisticians model it is it's a very simple assumption in hindsight. But as we'll say, in fact, it doesn't even show up when you design the algorithms, but it's always good to keep this in mind. And the assumption is that there is an underlying ground truth, which is what you're getting at. But I want to make sure that it's a ground truth distribution on training and test examples. Okay, meaning there is some distribution D on X. In fact, we're never going to know what, I mean, sometimes we know what this distribution is, many times we don't know it. It doesn't matter, but it's the assumption is that you have this sort of drawn okay. So to build our algorithms, we'll work in this idealistic scenario where we're going to assume that the training data examples are coming from independent samples from some distribution. Okay? So basically like saying, I have a whole database of images, I sample a few of them, I get their labels from it. And then to go along with it, the test is also from. So there is some underlying distribution, and our test and training examples are both coming from the same distribution. This is the basic setup. If you're taking an advanced class, then people also study distribution shift, where there is a difference in the distribution of test and training. And that's a major challenge when it comes to some domains. But the basic setup, which is pretty widely applicable, is both are coming from the same distribution. Okay, I mean, sometimes we know what the distribution is, sometimes we don't, but this is an assumption that we can. Okay. And this by itself is not enough. We kind of got to know that the training and tests are coming from the same distribution. But along with that, we'd also like to say that the labeling is not arbitrary. It's not something, ad hoc. Right? We have to make some assumption about what kind of labels we are allowed, right? And this is assumption 2. Okay, so there is some class of functions that we are going to use to make predictions. Right? I can't use, maybe it's going to be limited in some way, but we have to decide what model we are going to use. Maybe it's something as simple as a linear regression model. Maybe it's as simple as like a logistic regression model. Or maybe something very complicated, like I will use maybe a 10-layer convolutional neural network, right? But it's some model that I'm trying to fix to use to make the predictions. Okay. And with these two kind of assumptions, we can now formulate one version of learning, which I'll call learning as optimization. Okay. So recall we have an underlying distribution. Okay. And we have a data set. Right? And we have to come up with some model. Right? This is our choice, pick a class of models to use. Okay. And typically, these models or hypothesis functions will be parameterized by something. Okay, so let me just say something like this, theta. Okay, meaning there is some set of parameters which defines the model. If I'm using a linear regression model, it's just the weights of the linear, whatever your linear function. If I'm using a 10-layer deep neural network, then I need all of the weights in all of the layers. If I'm using a decision tree, I need to decide, which variables I'm going to decide on, right? So we're going for a very generic model, and then you can specialize it based on what this parametric class is. Okay. And our goal now would be to, you decided this, and the algorithmic task is find the collection of parameters which gives you the best performance in terms of prediction. Okay. So our input is going to be the data set. And then our output has to be which parameters which we are, do we think is going to be are going to give you very good performance. Okay. There's one thing that we have left out so far is how do you measure the performance of whatever model you pick. So if you do that, then I think we are, we'll be in good quantitative world where we can actually start talking about how to measure performance and how do you find the right model. Okay. So the question then is, how to measure and I mean, often this really has to be tied to the specific application or specific domain you're working with, right? Some loss functions or some ways of measuring performance are good for some specific applications. They're not so good for some other applications, right? And often this is really captured by this notion of a loss function. Okay. And what's a loss function? It just takes, it's some function which takes two labels and gives you a score. Okay, maybe your loss function is as simple as I want my label to match, right? If you get a mismatch of the label, then you get loss of 1. If you get the right label, you get 0, meaning you did well. Sometimes you might give you like a partial credit, right? If you call a cat, wrong breed of cat, maybe you get loss of 0.5, right? Whereas if you call it a completely different species, maybe you incur higher loss. Okay, so all of this can be, built into the model now by deciding what your loss function is. Okay, and so what would be the algorithmic task now? So our goal would be to something like this. The input is x1, y1, x2, y2 up to xn, yn. We have our data set as our input. And the ideal goal for us is to give me a set of parameters, right? Find a set of parameters among all the set of allowed parameters, which minimizes the loss function, okay, aggregated over my data set. Right? So if I use my predictor for x1, maybe it gave me some label. Did that label match y1? So what's the loss? What's the score there? Okay. And so I'll write down a formula and then we'll see what it means. And usually it's better to think of an average so that you're always working with some number that you can compare across data sets. Okay, so let's just parse this for a second. So this is my notation for H theta is the predicting model with parameters theta. Okay, so I'm trying to pick the best model, which gives you the best performance in terms of the predictions on the data set. And we already know the true labels of our data set, x1, x2, up to xn, but I want to see if I didn't know, but I used my prediction model, how well does it do? Okay. And as I said, we are averaging because, just so that we're kind of always talking about the same scale. Any questions about this? So quantitatively, it's very clear now. Given x1, given your data set, you decide a model, you decide a model class, hypothesis class, it's parameterized, you decide a loss function, and now you're in a quantitative world. My algorithmic task is to find this data which minimizes this. Okay, or at least gets as low a score as possible in terms of this loss function. Okay. Any questions about this? Okay, so this has a name, and this is used almost universally. It's called empirical risk minimization. Okay, so ERM. Okay, and it's called empirical risk minimization because, if you think about it, what we really care about is the performance of our model on unseen data, right? Whereas as I defined it, you're only checking its performance on the examples that you already saw. Right? Now, maybe I just memorize all of the answers, so I get perfect score on my training data set. But on a test example, I might do really bad. Right? There are very good tools within statistics literature to avoid such issues, you don't like memorize everything, but we are not going to address that. That's a very important part of statistical machine learning. And it's very important even for modern machine learning systems, but we're not going to address that. We're only going to focus on this optimization problem. Someone told us, or we decided based on other considerations, what model to use, what loss function to use, what algorithms are we going to use now, okay? So just to say, the ideal thing that we want is find the parameters which minimize what's called the population loss. And this is often called the training loss. So ideally, we would like to minimize what's, the loss that we would incur if I see a new example that is drawn from the same distribution, but we don't have access to that many times. So instead, you just say, okay, minimize the training loss, which is empirical loss, and there's this whole theory of statistical machine learning, which can connect these two things depending on your model. Okay. The model has some number of parameters. As long as the data set is sufficiently bigger, you can connect this to that. Okay. Any questions about this? Sorry? Yeah, so basically, if there's this notion of dimension of your model. So think of it this way, right? If your memory capacity is only 10 bits, but you're getting good score on hundreds of examples, then you must have learned something about the model instead of just memorizing the answers, right? Something similar happens in actual systems. There's this notion of dimension, the various notions of dimension, like VC dimension and Rademacher complexity and so on. If those things are reasonably small and your data set is bigger than whatever your dimension is, and then you can connect these two things. Okay. Yeah, that's a good question. Let me just say, there's this whole area of statistical machine learning. Which gives you various tools to connect training loss and population loss. And this is things like VC dimension, Rademacher complexity. I mean, I'm just telling you a few keywords. So in case you're interested, you can try to look up for them. Okay. But we're not going to focus on this. We're only focusing on the algorithmic part. Okay, yeah. Yeah, so I mean, technically, in fact, in the more general setting, you have to even consider the label. You can think of it as a distribution on X times Y. Okay, that's the true formulation that you have to use. In this one, I'm just doing it in a simplistic way. For two reasons. One, in terms of modeling, it's a little bit easier to understand. The other thing is because we're only focusing on ERM, it doesn't matter as much for us. It will matter when you're doing this connection between the two. It's a good question. Any other questions? And I mean, there's also kind of a different view of this empirical risk minimization. This is called the back learning model. But I think ERM is more useful, especially in challenging scenarios where we don't have clean solutions. Right? Okay. So let's look at some examples, and that will help us kind of gain some intuition of what we want to do. And then we'll see what's the most general algorithm that we can have. Okay, so what's the first example of empirical risk minimization? Okay. So the domain for this application is just going to be d-dimensional vectors. I mean, again, every image is at the end of the day encoded as a vector. And if I have a 1024 by 1024 image, then it's a vector of dimension 1024 times 1024. Right? For each pixel, if it's a black and white image, then I'll write down its grayscale value. It's a number from 0 to 255, right? So everything is a vector. I mean, maybe matrices or tensors, but at the end of the day, all of those are vectors in some space. Okay. And the labels are also just going to be real numbers. Think of them as scores. Instead of just giving it, saying it's a cat or a dog, maybe I want to say, give it some number which tells me what kind of label I want. Okay. And then the parametric family. That we'll use is linear predictors. Okay. So even the predictors are parameterized by d-dimensional vectors. Maybe, yeah, let me keep it simple. Okay, and given a collection of parameters, theta, okay, so maybe your vector has like, various like vital statistics. Let's say you have the blood pressure, maybe the heart rate, respiration rate and weight, height, and all of those things. And based on that, you're trying to predict some kind of, let's say, maybe the risk of suffering from something. Okay. And the way you're predicting is giving weights to each of these features and just adding them up. It could be positive, it could be negative weights. You're just giving some weights to each feature and then adding them up. Okay. And that's your prediction for what the label is going to be. And more generally, you can also think there is a constant term. I mean, nothing really changes. It just makes it a little more cumbersome to write down the constant terms. I'm going to avoid it for now. Okay. Maybe there's a constant term which you also have to add. Okay. And so we have the model, we have the domain and everything. What else do we need? The loss function, right? And based on the loss function, the problem can actually change quite a bit. So we need to decide what's the loss function. And one of the most often used loss functions is the squared loss, which is just how far are your two numbers squared. Okay. You tell me your prediction is 0.1, maybe the truth is 0.5, so then your score is going to be 0.4 squared. Why square? There are very good statistical reasons to pick square over other losses. I mean, in some applications, the other losses also make sense, but squared loss somehow seems to be more useful than others. So then what is the empirical loss? So often I'll use this big L. There should be a suffix of the data set because it depends on the data set, but usually it's fixed. So we have right, this is a function that we're interested in. And in our case, this is going to simplify to the squared loss, right? And so this is our prediction. This is the label. The squared distance between the two is the loss for each example, and we average it over all of the examples. Okay. So if you think of it as an algorithmic problem, then what's the setup? Okay, this is called least squares regression. One of the most, one of the simplest and also still, relatively widely used statistical models, least squares regression. You're given as input x1, y1 up to xn, yn, and our goal output is find theta to minimize let me use different letters. Yeah, actually, we'll use this notation of inner product. Okay, so theta comma x is just the weighted sum of the coordinates. Okay. So you're looking at the inner product of your weight vector theta with your particular example xi, and how far is it from the label? Okay, so this is what least squares regression is. Statistics 101. You're given this input, you want to find this output. That's it. Okay. And you can imagine there are other things you can try, like what if maybe loss function doesn't have to be the square. It makes equal sense to just look at the absolute value. Why are you taking the square? I can also ask what happens if I just want the difference between A and B in absolute value. In this case, our goal would be to minimize the empirical loss function, which is okay. And so using linear predictors kind of makes sense, especially when your labels are continuous. But what if your labels are discrete, meaning you only have, like, let's say, two labels, either cat or a dog. Maybe one of them you call 0, one of them you call 1, and you're trying to come up with a 0 or 1 label. So what are some modifications we can do here? What if labels are this? So meaning, maybe the label set has just two values, 0 or 1, cats and dogs. Or maybe it has like 10 different categories, 10 different animal species, things like that. So now we have to maybe change the parametric family a little bit. We can't just say, okay, take the inner product, theta comma x. If you're getting a real number, we have to somehow modify it to be 0 or 1 again, right? So one parametric family that is quite widely used in such a scenario is called half spaces or linear threshold functions. Meaning what you're doing is essentially computing an inner product or making a linear prediction as before. But if that value is more than some threshold, you'll say 1. If it's less than some threshold, you'll say 0. Think of it as like, maybe if it's more than 0.5, I think it's 1. If it's less than 0.5, I think it's 0. All right. So in this case, my prediction family is of this form. It's 1 if, maybe this is greater than some threshold t, 0 if is less than. Okay, this is a new prediction family. T. Yeah, sorry. Yeah, it's half spaces. Or these are also called linear threshold functions. Okay, you're computing a linear function and then thresholding at some value to make it discrete. You can, think of other kinds of thresholding as well. Right? And yeah, so we have to still, this is my new parametric family. Maybe for loss function, I can try I can just write the discrete loss, which is, okay, you incur a loss of 1 if you're wrong, you incur a loss of 0 if you're correct. Very simple. Okay. In this case, our ERM would be to minimize something like this. Again, the same thing as before. So E is h theta of xi equal to y. So in some sense, you're just trying to find the theta, which minimizes the number of misclassified examples. Okay, it's kind of a simple enough objective. And there are also, there are other loss functions people have studied. There's something called logistic regression. Where you think of your linear predictor as giving some probability estimation for what the true label is going to be. And there's something called hinge loss. And there are many other kinds of loss functions. Okay. Let me just define hinge loss because I think we will look at it as an example later on. So hinge loss is useful when the label is discrete, but your prediction need not be. Okay, I will draw a picture to make it clearer, but let me also write it down just in case. So, okay. So imagine your label is like positive, right? B is like 1 or something. Then maybe if my prediction is more than 1, I'm happy. So meaning I get 0 loss. But in the threshold function, as long if I'm at 0.9, even then I'm getting full loss. Whereas maybe I should give myself some credit for getting close to the value 1. And the linear predictor said, okay, it's 0.9, you round it, then you get something. So hinge loss kind of interpolates between this. As you get far away from 1, you incur more and more loss. Okay. And if it's more than 1, I don't incur any loss. Okay. And the flip side, if B is 0, you have to kind of change the curve. Okay. So the summary is that you can pick various parametric families, various loss functions. These are often tailored to the specific application you have in mind, but for every one of them, you end up with an empirical risk minimization problem that we are looking to solve. Okay. So from our perspective, learning is equivalent to solving this optimization problem, which is find me some set of parameters which minimizes the empirical loss. Okay, that's what we're trying to do. And that's what we're going to address in the next 3 or 4 lectures. We'll try and think of generic strategies for solving such minimization problems. The first thing to keep in mind is that often in this setup, we're working with a continuous set of parameters. In some cases, you have discrete models like decision trees or something like that. But if you have, let's say, linear predictors or convolution neural networks or things like that, you have a continuous space of parameters. Okay, so these are weight vectors, they are real numbers, and you have to come up with a way to do that. And the abstraction that we will use for that is even forget. Let's forget this learning problem completely for a little bit. We'll come back to it as applications, but what if I just tell you there is some function L? It takes, imagine our set of parameters is there are D parameters in our parametric model, and it takes a set of parameters and gives it a score, which is this loss function. Okay. I mean, our loss function has some specific structure, which is often useful, but let's not worry about it for the time being. And if I just give you this loss function, are there generic tools for minimizing this loss function? Okay. And we also have to be a little bit more careful in general, because maybe not all parameters are valid, right? Like if you're trying to give some prediction for some things, maybe you don't want to get negative predictions. There's some constraints on the model, but let's work in the unconstrained setting where any set of parameters are fine. And this is called unconstrained optimization. Okay, so you have some loss function L, some cost function, and you're trying to find a set of parameters to minimize this loss function. And this view will lead us to a meta algorithm, which, as we'll see, is very useful. Okay, let me make it even simpler and suppose your loss function is one dimension. Okay, so I have only one parameter that I'm trying to figure out. Okay. So maybe my function looks something like this. Okay, so this is my L. Okay, so this is my L. I'm trying to find where this is minimized. I mean, in this picture, it's kind of clear. It should be this point. So I have some kind of access to this function. Typically, the kind of access you have is that you don't have complete description of the function. The kind of access you have is, okay, give me a set of parameters. I can tell you what its score is. Okay. Maybe I can also get some other information about the function, but we don't have a complete description of the function itself. So how do I find this point based on knowing something about this function? Okay. And in this general setup, there is a very simple strategy, which actually is very useful. It's really just a greedy algorithm. And the greedy algorithm is as follows. One analogy is like, imagine you're trying to climb down a hill. For some reason, you're stuck on some mountain. It's very, very foggy. You can't see too far. But you want to go to the bottom of the hill. Okay. Imagine this is a landscape, right? Really think of this as the landscape. So this is the mountain ridge that you're on. And maybe you're somewhere here. Okay. And obviously you don't have a full global view. That's kind of comes from actual limitations and how much knowledge we have about your loss function. You have some kind of view, but maybe I can evaluate at various points. Maybe I can know what it looks like around me, around where I am, but I want to get to the bottom. right? So you have a mountain, or not a mountain, but like a mountainous landscape. It's very foggy. You have some kind of, visibility range, let's say 10 feet or something, and you have to get to the bottom of the hill. What would you do then? What's a natural strategy that one of you were to try? Any suggestions? And if you've ever been stuck on a mountain? Yeah. Exactly, right? Somehow, if you look around, there's some direction which is going down, just try and go down. It's as simple as that. You want to go down, just go down. Right? But you have to pick, maybe it's a three-dimensional landscape, right? There are multiple things that might take you down. Okay. So, okay, so the first idea is, as we said, pick a point. Pick a starting point. This is basically like, where you're starting on the mountain range, right? And then move in a direction that reduces function value. Right, so we're thinking of the function, really the loss function, as kind of height from your sea level, right? I want to get to the point which has the least height. Okay, and if you think of like a 3D mountain, and I mean, when we see demos, it will be clearer. But let's say since I'm not demoing, but just drawing here. From somewhere here, depending on, it's like you're in some bowl, right? The bowl need not be like a spherical, like completely symmetric or anything. It might be more pointy in some direction. It may be flatter in some directions, right? So which direction should you choose to go down on? There are many choices. I can go down this way, maybe this way, maybe this way. Which direction should I pick? If you're actually on a mountain and had to do this, what would you do? Yeah. The steepest. I mean, you'd be greedy, right? Let me move in the direction which gives me the most bang per buck, in the sense that it takes me down the most in terms of the amount I actually move. If I take a single step, 1 foot step, which direction takes me down the most? Maybe something only has a slight gradient. If you're on a hill, there's a slight slope. If I go in this, it's only going a little bit far. Whereas maybe in here, it's very steep. I just try and go down this way. Okay. So let me modify this idea now to say, move in a direction that is, okay. Rephrase, move in a direction of steepest descent. Steepest descent meaning, it gives me the most bang per buck in terms of decreasing the height compared to the distance I travel. Okay. And fortunately, we exactly know what's the direction of steepest descent. And this goes back all the way to maybe like 300, 400 years, since we know what's the direction of steepest descent. So what is this direction of steepest descent? Can anyone tell me? Yeah. Well, I mean, if you're in a 3D landscape, there are many, you're really on a hill, right? So there are various directions. Some things might be steeper, some things are less steep, right? Yeah. If you look, you would know, but your knowledge of the landscape is kind of, is limited, right? So what would be the direction of steepest descent? If you had to do it like quantitatively, yeah? The gradient. So this is actually like calculus 101. And if you ever wonder what calculus was good for, this is one of its amazing applications. Claim the direction of steepest descent is the negative gradient. Okay, so let me so basically, if you're in 2 dimensions, it's kind of clear, right? If you're here, you move in whichever direction reduces the function value, right? But if you're here, there are 2 directions. The function value is actually decreasing in both ways, but maybe on one side you're falling off steeper than the other. In 3 dimensions, of course, there's a lot more chance of different directions giving you different rates of decrease. Okay. And the gradient, if I have a function from, let's say, d dimensions, then the gradient at a point is the vector of partial derivatives. Okay, so you have a vector of partial derivatives, and this vector, the negative of that, tells you which is the best bang for buck direction to choose. Okay, so if you take a 1 foot step along this gives me the most decrease in function value. Okay, so if we combine this with our greedy idea that I start from some point and then just start taking tiny steps or some steps along the direction of steepest descent. I mean, this is kind of a very, you might think it's a short-sighted view, right? If you're really stuck on a mountain, you wouldn't do this, because maybe if I keep going the steepest direction, I get stuck somewhere, right? But given limited knowledge, that's a fair strategy to adopt, right? So this leads us to a very important algorithm. You should really think of it as a meta algorithm, because it's not just a single algorithm. Like, it's almost like you can adapt it to various settings. So this is a gradient descent algorithm, or GD, right? So you pick a starting point using something, say theta 0, and then for some number of steps, I just do the update from your current point, move to a point which is a step along the gradient. Okay. And this eta is called the step size. And the intuition is like, sometimes you don't want to overshoot, right? So the step size has to be chosen with care. Like, let's say I'm somewhere here, and I can take a step around the gradient, but if I take a long, big step, I might end up here, right? Which did not result in a decrease in the function value, or the best decrease in the function value, right? Whereas on the other hand, if I take a very, very tiny step, maybe I'm not making as much progress as I could. Okay, so you have to somehow tune this parameter, step size, but we'll just take it to be constant across iterations for now. Typically, if you take any sort of machine learning system like PyTorch or TensorFlow, they will choose the step sizes and everything for you. Okay, but as I said, we are going to look under the hood and see how these things are done. All right. So very generic algorithm now we can apply to any empirical risk minimization problem, as long as we can evaluate the gradient of the loss function. Okay. So what kind of access do we need for the loss function now? We need to be able to evaluate the gradient of the loss function. Okay. Any questions about this? Okay, so let's, maybe think about, as an example, so what did we have? Gradient descent has nothing to do with ERM, empirical risk minimization. You can apply it to any, continuous optimization. Right? As an algorithm, it's applicable. Whether it's good or not is a different story that you have to study. But I can definitely apply it to empirical risk minimization problem. So maybe let's say we'll try and do that. And one reason why it's actually very nice for ERM is the gradient kind of simplifies a little bit. Instead of computing the gradient of the average, I just need to compute the gradient of each individual loss, for an example, and then take the average across all of these things. Okay, both give me the same expression, right? Because gradient is a linear operator. If I take sum of two things, the gradient of the sum is just sum of the two gradients. Okay, and you can often use chain rule to simplify this further. Like the theta here is only appearing in H. So you can use the chain rule to compute this. But again, we're going to assume that you can compute the gradient easily. In fact, for many systems now have autograph tools, which if you give me the cost function, they'll actually compute the gradient automatically for you. You don't even have to program it. Okay, but sometimes you can have faster algorithms for computing the gradient and so on. Okay. Okay, so let me say a couple of things about this. One is, okay, so all of this is good if your function is differentiable, right? But what if your function is, not all functions are differentiable, right? this is a pretty nice function, nice looking function, but this is not differentiable here. It has this kind of discontinuity in its rate, but technically it's not differentiable. There's no gradient at this point. Okay, but even then you can apply gradient descent in a different form. So what if L is non-differential? Right, here it's not differential. Nevertheless, what you can do is use something called a subgradient, and so the rigorous definition requires a little bit of work, but I'll state one stated definition which is pretty broadly applicable. There are some border cases you have to be careful about. Basically, subgradient is a direction where it's as if I can draw a line which lies beneath my function curve locally. As long as I can find a line which lies beneath my function curve locally, that is as good as a gradient. Okay, if the function is actually differentiable, the only allowed line will have slope, which is the actual gradient. But if there's a discontinuity like the one here, then I can pick any one of these lines and the same sort of intuition is still applicable. Okay, so in particular, a direction G is a subgradient of f at some point x0 for all x. If I take the line with slope g at x, it lies completely below the actual curve. Okay, and you actually don't need it everywhere, you only need it locally. But again, that's a technicality, so don't worry too much about it. The point is that even if you're, like if I take the absolute value function, so what does it look like? It looks something like this. Okay, this is the curve of absolute value of x. And again, it's not differentiable here. Right? And but nevertheless, you can use gradient descent as long as at this point you use any one of these slopes is fine. Okay. The point is moving along the gradient can decrease the function locally, and that could be true for other lines when there's a discontinuity. Okay, all of these are called subgradients. Yeah. That's a good question. Like, we're actually working in a much more, easy setting where the parameter space is the entire space, right? That's why I call it unconstrained optimization. So discrete is like an even harder setting where you have to be a bit more careful, right? In some cases, even if it's not the entire space, but just tell you, okay, the parameter values cannot, maybe the first weight cannot be more than 10. Right, then you have to be again use a different algorithm. Okay, so we're working in the unconstrained setup where the weight vectors can be anything, and in general, if there are some constraints, you can adapt gradient descent to that. Okay? But actually, gradient descent by and large is much more useful when the parameter space is continuous. Even if it's constrained, it's fine, but continuity is helpful. Any other questions? So we now have a meta algorithm. Give me any loss function that you want to minimize. As long as I can compute the gradient or subgradients in some cases, I have this algorithm that I can use. Okay. So subgradient descent would just be the same as gradient descent, but instead of using the actual gradient, I would pick the subgradient. It only comes up in a few cases like the absolute value function, and other. So we can use a subgradient as a substitute. Okay. All right. So now we have the basic setup of gradient descent, but we would like to know how well does the algorithm perform, right? So what are some things that we would like to do? So what would we like to say or know about the function? Yeah. Yeah, that's kind of the most important question that we would like, right? Maybe even does it or will it? Will gradient descent get me to the true minimum? Yeah, it's not true that you'll always get to the true minimum, right? imagine even in this curve, if I start somewhere here, I start doing gradient descent, I keep going, I end up here, the gradient is 0. And I stop making updates. I'm not getting to the minimum. Okay. So when or can we find some conditions under which you can get to the true minimum? Maybe I don't want to get to the true minimum, but at least can I get to a value which is comparable to the minimum? I don't want to be completely off from the true minimum value. Okay, is there some way to quantify how good your performance is? What other things would be like? Yeah. Yeah, I mean, how many steps do you need? And if it can get to the true minimum, but if it takes forever, that's pointless too, right? So we need to know how many steps would GD take to get to the minimum. But maybe, since we don't know it will get to the minimum, you can ask how many steps would GD take to maybe reach some kind of stability, right? Maybe at some point it starts updating. If it goes in a loop forever, that's kind of really bad. But if it converges, meaning it reaches some kind of stable thing, take to reach some sort of converging points. Converging meaning you're not making big updates anymore. So this is called the rate of convergence. You want to know how fast would you get to the minimum or a point where you stop making changes. Okay, what else? If you were to actually code up the algorithm, there's something that we didn't discuss at all, right? Yeah. Yeah, I mean, that's also important, right? So far we are assuming that the gradient is something that right? But computing the gradient itself is another algorithm. That's why I said it's like a meta algorithm. And often you need another algorithm that computes the gradient for you. Not as if you always have a simple formula to code it out. Okay. So how to compute the gradient in the first place? If it's a simple thing like linear regression, we can use like, calculus 101 to compute the gradient using chain rule. What if it's a 10-layer convolutional neural network? How do I compute the gradient then? Okay. What else? Yeah. Yeah, so I mean, that's kind of connected to how to compute the gradient, right? Like, I can compute the gradient, but what's the cost of the gradient? If the gradient is very expensive, is there something cheaper I can do, but is kind of similar in performance? Right? All of these are important questions. Depending on the application, they will show up. Okay. What else? Yeah. Picking the step size, that's also very important, right? So how to choose the step size. In optimization optimization language, this is called a hyperparameter, meaning something that it's not so easy to train that you have to pick the step size by using some kind of hunch you might have or some knowledge of the domain or something about the function. Yeah.
Gradient descent algorithm you should use, what are the like Nesterov, Adagrad?
Right. So that's again, right now we're starting with just the simplest one, right? Gradient descent, and we'll see like, when you would modify it and how you would modify it. And many times all of those things are connected to just, kind of choosing the step size and other stuff. Okay. I mean, gradient descent, as you can see, is a very simplistic algorithm, right? You're just taking a very simple, like a greedy step. Even that is pretty hard to analyze as rules. And there's some interesting questions. How to choose a step size is very important practical. Okay. How do I compute the gradient? What's the cost of computing the gradient? Are there some things that I can use to minimize the cost of the gradient, but they're still kind of useful or similarly useful as computing the gradient? there are other things like, maybe something that you haven't talked about is how to pick the starting point. Sometimes it can make a big difference how to pick the starting point. You might use a completely different algorithm to arrive at a point, which is a good starting point, and then use gradient descent. Okay. Can you imagine maybe I run some kind of different initialization algorithm. If I start from here, then I won't converge to the true minimum if I use gradient. But if I start here, I would converge. Okay. So these are things called like warm start, meaning somehow I pick a starting point which is somewhat close to the minimum, and then gradient descent can like boost me all the way down. Okay. So that's also an important consideration in some applications. What else? I mean, maybe this is kind of one of the easier things to answer is when do I stop? Like, maybe at some point I stop making progress, or I detect that I'm not making progress. Or maybe I just run it for like, okay, 1,000 steps. That's my limit. That's the amount of computational budget I have. I'm just going to do that. Okay. And let me also say, kind of related to this is if gradient is expensive to compute, can I use any service? So what we'll do over the next lectures is first kind of try to answer question number 1 and 2. It'll give us an idea of all of the other things, kind of tells us, okay, how to choose the step size based on something, and when to stop. And also studying these things will tell us, okay, even though we'll make some strong assumptions, they'll give us general modifications of gradient descent, which do well even when those assumptions are not met. Okay. So we make these assumptions to make kind of a toy problem that we can analyze. And from that, we'll draw algorithmic insights, which can then go and deploy in the wild to actual sort of real world problems. Okay. So let me say, let us first find some nice conditions. Let us first try and find some nice and somewhat like, at least one of those will be necessary conditions to figure out when GD would work. Okay. And this will suggest us modifications and other things to try. Okay. So let me, state one condition, which is quite natural. And then the other ones are kind of, I think, require some deep insight, but are really powerful. Okay. So the first one is, if you think of your function, right? Let me draw two functions. Okay, so my first function looks something like this. Okay, this is the first function I'm trying to minimize. The next one is which do you think is easier to minimize? Which would be easier to run gradient descent on? The left one, right? Why? The second one is too wiggly, right? So you have to take very, very tiny steps to not overshoot things and so on, right? And the way kind of, mathematically to say it is how sensitive is your function to local variations. If it's kind of very wiggly or small changes can lead to big spikes, that will make your problem harder to solve, especially if you're using gradient descent. That means your step sizes have to be very tiny. Your initialization point can really change where you're, how well you converge and so on, right? I mean, if you really think about it, what if it's something even nicer would be the nicest function to minimize is the parabola. The gradient descent will be very nice here. The other two not so much, but the right top one is the worst. Okay. So the first sort of necessary thing that we can quantify is how sensitive is your function. Okay, so how does it respond to small variations in the input? If small changes lead to big changes in the output, it's a harder function to optimize. Okay? But for gradient descent, often along with just the simplistic notion of sensitivity, we also talk about some other properties which are helpful in practice. So when we come back next lecture, we'll try and quantify this intuition that, okay, less sensitive functions are easier to optimize. And some kind of assumption on this is necessary for GD to work. Right? If you just spike here all over the place, there's no hope of GD to work. So let's quantify some cases, some way to make it quantifiable. Okay. All right, so let me stop here. And next class we'll take up with this question. We'll start with this question of how to quantify sensitivity and see its impact on GD.